Morning. So today your homework was chapter 17, problems 16, 20, 22, 24, and 45. So let's go ahead and go through each one of the problems individually. So this is number 16. 16 has to do with the common ion effect, and we're dealing with a bunch of weak acids here. And so the main point here is when we set up our ICE table, we know we're going to have a little bit of the conjugate base of the acid on this side initially. So let's see what that looks like. So A says, use the information from Appendix D. So I went up to Appendix D and I looked up the Kas or Kbs of any of the weak acids or bases that we're dealing with in these problems. So use information from Appendix D to calculate the pH of a solution that is 0.250 molar sodium formate. So let's go HCOONA, and 0.100 molar formic acid, so HCOOH. The first thing I'm going to do is look at these two compounds, and I'm going to figure out, okay, what is the conjugate base here? And I see it's this part of the salt up here. And then here I have my acid. So I went ahead and looked up the Ka for HCOOH, which is my formic acid. And the Ka is 1.8 times 10 to the negative 4. Okay, so I have everything I need to be successful in this problem. All we're going to do is set up an icebox problem for formic acid breaking down and that's it. So initially for formic acid I have 0.100 moles per liter. Here I have 0 moles of H plus initially, and I also know that I'm going to have 0.250 moles per liter of COOH, because that's what we put in the form of the salt. So we're just pretending that this breaks down immediately into all of that, because that's all we really care about here. I know that it's going to change by X in some way. And remember, because it's a weak acid, we can ignore it here when we do our change, except for the H plus. So this really is minus X and plus X, but remember, it's going to be so small, it's not going to make a difference. And all I do is plug it into the Ka equation and solve it. Rearrange, solve for X, and X I get 7.2 times 10 to the negative 5. And this is equivalent to my H plus concentration here. So I'm going to get my pH is negative log of this, and I get 4.14. And that's my pH. So that's A. Let's try B. A solution that is 0.510 moles per liter of pyridine, C5H5N, plus 0.450 moles of pyridinium chloride, C5H5NHCl. And so for this problem, I can see that I have the salt here, right? So you might not know what these things are, right? But that's okay. What's important is this concept that when this Cl breaks off, this is going to be positive. And that this is the conjugate acid of this weak base. And you might have to look at this a second and figure that out if you're not familiar with what these things are, right? So I know that if I look up the Ka or the Kb for pyridine, and again, you're not going to look at this and be like, oh yes, pyridine is a base. But when you look in the K, or in the appendix D, you notice that there's a Kb for it, and the Kb is equal to 1.7 times 10 to the negative 9. And you'll also notice the salt of this has one extra proton here, more than pyridine. Okay, so we're going to just set up our ice table. So we're going to have C5H5N. In this case, it's a base. So when I react it with, H2O, when I react it with water, we are going to get C5H5NH plus, which is that conjugate up here, plus OH minus. So in this case, we're going to have to solve for the concentration of the hydroxide ion and then solve for pH from there. So initially I have 0.510 moles per liter. Water we're going to ignore because it doesn't matter. And I have 0.450 moles per liter of this ion. And 0 OH. So it's going to change by some quantity of X. And again, I can kind of ignore it down here, right? So it should be minus X, but we're ignoring it. And then we solve for X, so Kb through the Kb. I think the most complicated thing about this problem is realizing that it's a base and that you need to solve for OH and find the Kb. It's exactly the same thing, it's just a little bit different. So when I rearrange here to solve for X, I get X is equal to 1.927 times 10 to the negative 9. And I know this is equivalent to my concentration of OH. So if I solve for my POH, I think that's, for me, the easiest way to go about it, is to just figure out what the POH is. And I get that it's 8.715. And then remember, to get to my pH, I'll just go 14 minus 8.715. And that's going to give me 5.29, which is my pH. Let's go on to number 3. Or, I'm sorry, C. So C says, a solution that is made by combining 55 milliliters of 0.050 molar hydrofluoric acid, HF, with 125 milliliters of 0.10 molar sodium fluoride, NaF. So what do I have here? I have a weak acid, so remember HF is weak, and its conjugate base. So HF reacts to form H plus F minus. And we'll set up our ice table. But there's one thing in this problem that is different about the other one, and that's the fact that we have different amounts of different molarities, and so to just plug these right in here isn't going to work. The first thing we need to do is figure out how many moles exactly we have. Then we can plug that into our equation. So here I have 0.050 moles per liter, and I'll just write that out, moles per liter, and I have 55 milliliters of it, so that's 0.055 liters of HF. So I'm going to have to do a little math there. And I should get 2.8 times 10 to the negative 3. And that's of HF, so we can plug that right in up here. I'm just going to write it out like this, 1, 2, 8, okay. Same for NaF, so we're going to solve for moles. 0.10 times 0.125 liters. I'm sorry, moles per liter. And that should give me about 0.013 moles of F minus. And I need to be careful here and write moles because that's not the molarity, right? We know what our total volume is if we add it up. But right now we're just working in moles. Okay, I know that this is going to change by some amount of X. Again, we can ignore it. So I could write minus X and plus X here, but it's not going to do anything. And I'm going to look at the Ka in Appendix D and find that it's 6.8 times 10 to the negative 4. And then I just solve for X, just like before. And X equals 1.5 times 10 to the negative 4, which is equivalent to my concentration of H plus. And so therefore my pH, if I get the negative log, is 3.83. That's my final answer. So you can see all these problems are similar. Each one is just slightly different. So in A, we were just solving for a weak acid, and they gave us the concentrations. In B, we had to use the KB and kind of work backwards from OH. And in C, we had to figure out what X was. We had to figure, but initially we needed to figure out how many moles we had. And I think, let's see. And then ultimately, hold on a sec, I think I skipped a step down here when I was showing you point. Let me solve for this. Point 12368 times 0.0028 divided by 0.013. So that is right, but then I need to divide it by 5. Answer divided by 5. Hold on. Let me check my work on this one. So in this case, I would, when I solve for x, I would need to, which this is what you get, and this would be not the concentration of x, but this would be the moles of x, or H plus, right? Dang it, I don't want to ruin my whole video just for this problem. So this would be the moles of H plus, and I believe that you would need to divide it by the total number of liters that you have, which would be 0.055 liters plus 0.125 liters. Did anybody catch that? So that's what I would do, and then you would get moles of H plus per liter. So if I were to do that, I would get, let's see, 0.00015 divided by 0.055 plus 0.125. And I would get 8.3, so the concentration of H plus would be 8.3 times 10 to the negative 4. And then our pH from there would be equivalent to, 3.08. But that's not what the book says, so I need to double check that answer. If anybody else can see anything different in this equation, let me know and we'll talk about it. Okay. Anyway, that was problem 16.